Welcome to lecture 2.6 covering implicit differentiation. Sorry for a little bit of background noise in the mic. I tried it with different settings and could not come up with anything any better. So hopefully we'll get through this okay. So far we have been dealing with explicit functions, okay? And what that means is simply functions that can easily be defined in terms of x alone. So a function would be f of x equals some function of x, y equals 2x plus 4. This means that we can solve the equation for f of x and only have variables of x in the equation, okay? So this is an example here. So we have y on one side, or f of x, because this is the same thing. And everything on the other side is a function of x alone. That's what an explicit function is. So when we take the derivative here, we just simply take the derivative with respect to x, and it's pretty simple and straightforward. Some equations aren't possible or not very easy to state in explicit form. So look at this equation here. So notice here I have x cubed plus y cubed is equals 6xy. It would be very difficult to define this equation in terms of y equals and everything else on the other side being x alone. Notice if we solve the right side of the equation for y, we still have y's on the left side. And that's what's called an implicit equation or implicit function. And what it means is we don't have all the y's on one side and all the x's on the other, or really more accurate, we don't have y equals everything is a function of x, okay? But we still know that if we change the value of x, that this will impact the value of y. So we know that y is related to x implicitly, even though it's not explicitly defined as y equals x plus 2, etc. Okay? Specifically, this says that changes in x correspond to changes in y. So, again, we say that y is an implicit function of x because we know that as x changes, y changes. Okay? And there is a way to take the derivatives of these functions, and we call this implicit differentiation. It's pretty straightforward, and I'm going to hopefully give you some shortcuts that your book, I think, does not such a good job of explaining. Anyway, so notice here we have an explicit function. We just looked at this a minute ago, I think. And notice that if we take the derivative, if we want the derivative of y with respect to x, dy dx, which is just notation, which is the same thing as y prime, right? These first two are just notation. And if we take the derivative here, we get the derivative of 1/4 x is 1/4. The derivative of 3 is 0, so 1/4 plus 0 is simply 1/4. Now notice, this is a linear equation in slope-intercept form. This over here in yellow is the exact same equation in standard form. In standard form, this is a linear equation. In standard form, we have all the variables x and y on the left and the constant on the right. And so if we multiply this equation by 4 and then get x and y on the same side, and typically we always put x as positive as possible, and then the constants, you'll get the same equation. So I'm not going to go through the algebra of converting this to this. You should be able to do that. So when we're doing implicit differentiation, we take the derivative of both sides with respect to x. Okay? So this is saying take the derivative with respect to x of the left side, and this will equal the derivative with respect to x of the right side. And again, this is nothing new for us algebraically, right? If we do something to the left, we need to do that same something to the right. Okay? Since we know that y is a function of x, we use the chain rule. So remember, the chain rule says we can take the derivative with respect to something else. In this case, we can take the derivative with respect to y, and then take the derivative of y with respect to x. Okay? So first of all, we've separated the difference. We're taking the derivative with respect to x of the first term minus, we pull the constant 4 out. This is one of our derivative rules, right? We can pull the coefficient out in front. And then we take the derivative of y. Now because it's y, again, what we're going to do is take the derivative with respect to y of y, and then take the derivative of y with respect to x. Notice on the other side we have the derivative of a constant, which of course we know is 0 by now. Okay? This is where you're actually using the chain rule, and this is again a nice, really magical is what I call it, but it's almost an intuitive part where the notation works like a fraction, and so these derivatives with respect to y, dy's, kind of cancel out, and we're just left with the derivative with respect to x, y, which is what we're looking for. Okay? So when we solve this, the derivative of x is 1, minus 4. The derivative with respect to y is also 1, so it's just the same thing here. And then we have dy dx. What we do then, once we've kind of simplified this, we simply solve for dy dx because that's what we're looking for. We're looking for the derivative of y with respect to x. So what we have set up the equation, now we simply solve it. So we get 1 equals 4 dy dx, so dy dx equals 1 4. All I've done is add 4 dy dx to both sides, and then I've divided by 4 to solve for dy dx. And notice, we get the same answer that we got before. Excuse me. Sorry about that. Alright. So let me break it down for you. Whenever you take the derivative of a y expression, it's basically the same as differentiating normally, then tacking a dy dx or y prime. I like to use y prime. It's easier to see in equations for me. And we just we add a y prime at the end of each of those expressions. Okay? So notice here, this is a very simple derivative. The derivative with respect to x of 2x cubed. We pull the exponent down in front, so we get 6x squared. By now this should be pretty straightforward, and with our shortcuts it's even easier. So notice if I take the derivative with respect to x of a very similar piece to y cubed, I take the derivative with respect to y, which would be the same as if the variable was x and it was just dx. So I get 6y squared. Okay, so I just pull the exponent down and 1 less for the exponent, and I add the dy dx. So both of these are the same. This is why I like to write it here. And then I would solve for, y prime. Okay, so take the derivative. When you have a y term, you're taking the derivative with respect to y, and then add a dy dx or add a y prime. Again, I like to use y prime because it's simpler notation, and then eventually we're going to solve for this at the end. So let's look at some examples. X squared plus y squared equals 25. Okay? So again, the first thing we're going to do is take the derivative with respect to x at each side. This means we've got a sum here, so I can separate it. So I'm going to take the derivative of x squared plus the derivative of y squared, and the derivative of a constant is equal to 0. So I've already substituted that in. Okay? Now remember that the derivative of y squared is equal to the derivative with respect to y of y squared times dy dx. So I get 2y dy dx. Okay? So again, when I'm taking the derivative with respect to x of y squared, I first take the derivative with respect to y, which is very simple, just like it was with x, and then I add a dy dx or a y prime. Okay? So remember, here I have 2x, the derivative with respect to x is 2x. We just saw the derivative with respect to x of y squared is 2y dy dx. And now remember, I solve for dy dx. So I get dy dx. If I subtract 2x from both sides, then I divide by 2y, I end up with negative x over y. So I've taken this equation and I've solved for dy dx or y prime. Again, 2y dy dx equals negative 2x by putting it on the other side, and then dividing negative 2x by 2y, I get negative 2x over 2y, and the cubes cancel out. Okay? So this is our answer for A, find dy dx. B says to find the equation of the line. Okay? So now what we have to do is find the slope, and then plug it into the linear equation. Okay? So It says at the point 3, 4. Well, remember this is x equals 3, y equals 4, so I just plug those values in and I get negative 3 over 4, negative 3 over 4. Okay? Remember our equation is y minus y1 equals slope times x minus x1. And so I have it here. And I could simplify that equation by multiplying this out and adding 4. And you may have to do that in your homework. Okay? But right now I'm okay with this. So finding the equation of the tangent line is pretty simple. Once we've found the derivative, we plug in the value of the points and then just plug it into the simple point-slope formula. So let's look at another problem. This one's a little bit more involved. Okay? This is actually a shape called the folium of Descartes. And unfortunately, I don't think I actually printed it here. I would have liked to put the graph up there so you could see it. First, we want to find y prime is x cubed plus y cubed equals 6xy. Okay? We're going to walk through this one a little bit quicker now. I know we haven't done, but let me do it a little bit. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared y prime. Again, I take the derivative with respect to y, just follow the derivative rules, and then I add a y prime. Now here it's a little more complicated, because now I have a product rule. So I have 6 times the derivative of x, which is 1, times the other term, y. So I get 6y. Plus 6x times the derivative of y. Well, the derivative of y is 1y prime, right? The derivative of y is 1, and then I add a y prime, so I get 6x y prime. Remember the product rule says the derivative of the first, which would be the x, times the second y, plus the derivative of the second y, times the first. Okay? So once I've got it, once I've taken the implicit derivative, I now have to solve for y prime. Okay? So this means I need to, well, actually here, what I've done is I've noticed there's a coefficient of 3, a common factor of 3 throughout this, so I've factored that out. And so it just makes the equation a little bit simpler and in more simple form. Okay, now that I've simplified, seeing there's a common factor of 3, I want to solve for y prime. Okay, so the first thing I want to do is get all the y primes on one side, and so I have y squared y prime minus 2xy prime. And anything that doesn't have a y prime, I want on the other side. Okay? Students often have a problem solving this equation for y prime at this point, but notice that y prime is common in all the factors on the left. That's why we moved them there. So we can factor out a y prime, and we get y prime times y squared minus 2x equals the right side of the equation. Well, now it's simple to solve for y prime. I simply divide by the expression in the parentheses. So y prime equals 2y minus x squared over y squared minus 2x. And this is our answer to A. Okay? The answer to B is asking us to find the tangent, and all that means is to find the equation of the tangent line at a point, 3, 3. So the first thing we're going to do is plug in the values, 3 for x, 3 for y, into our y prime, so we can find the slope. When we do that, we get y prime equals negative 1. Now it's very simple. Remember, it's y minus y1 equals the slope times x minus x1. And so we get this equation, which simplifies to x plus y equals 6. Okay? So when trying to find the equation of a line, or the tangent, which is the same thing, equation of a tangent, find the slope by plugging in the point values into your derivative formula, and then just do y minus the y value given equals the slope times x minus the x value given, which is usually given in the form of a point. Okay? Alright, let's move on a little further. The last question asks us to find at what point in the first quadrant is the tangent line horizontal. So we're in the first quadrant, so this means x and y are both positive and greater than 0. Okay? So remember that the tangent line horizontal means that the tangent or the slope of that line is equal to 0. The slope of a horizontal line is equal to 0, which means that our derivative is equal to 0. Okay? So the tangent line is horizontal if y prime equals 0. Notice if we set this equation equal to 0, we could cross multiply and that gets rid of the denominator. Or we could also realize that this whole fraction is going to equal 0 when the numerator equals 0. And that's what we have here. That y prime will equal 0 when the numerator equals 0. Because if we have 0 divided by anything, we have the whole equation equals 0. So when I solve this for y, I get y equals 1/2 x squared. Okay? 2y equals x squared, so y equals 1/2 x squared. Okay? Now I want to find the points for this, and remember we're talking about the points on the original equation. Okay? So I know that the y value is 1/2 x squared, so I plug that back into my original equation. Because that's the one we're using. We're trying to find the x and y points. So I get x cubed plus 1/2 x squared, because that's what y equals, cubed. 1/2 x squared cubed, because that's our original equation. The cube comes from the original equation. And this all equals 6x, again, times y, but for y we put in the 1/2 x squared. Now it's just algebra, and we solve algebraically for x, and we get x equals x to the 6 equals 16x cubed, or 2 to the 4 thirds. If we plug this into 1/2 x squared, we get 1/2 2 to the 8 thirds x squared. If x is 2 to the 4 thirds, then y is 2 to the 5 thirds by plugging it into this equation. Okay? Now you might ask why they left it that way, and I'm okay if you made this into a decimal and then plugged it into 1/2 x squared. That's fine. That's very fine. So the horizontal tangent is at 2 4/3, comma 2 5/3. 2 raised to the 5/3 power. Or you can see the decimals here. It might make you more comfortable just to put it in decimal form. And that's certainly fine. Alright. Let's look at another problem. Okay, we're going to do these problems with trig functions exactly the same way. Notice that we have x and y's on one side and x and y's on the other, so this is one of our clues that we're doing implicit differentiation. We're going to take the derivative with respect to x of both sides. Again, I've gone through this pretty quick. Notice on the left we have a chain rule. The derivative of the outer is cosine x plus y. Okay? The derivative of the outer function is sine x plus y. The inner function is x plus y. Okay? So the derivative of the outer, cosine x plus y. The derivative of the inner, the derivative of x is 1. The derivative of y is 1 y prime. Remember, whenever we take the derivative of y, we take the derivative with respect to y, which is 1, and then times y prime. So we have this here, cosine x plus y times 1 plus y prime. Now be careful, this is not a product here. This is the cosine of x plus y times, now it's a product, 1 plus y prime. So be very careful here. This argument can get confused with a product. We're multiplying 1 plus y prime times the cosine of x plus y. On the right side, we have a product rule. So the first term times the derivative of the second. So y squared times negative sine x plus the derivative of the first term, 2y prime times the second, cosine x. Okay? We're trying to solve for y prime, so we need to get every term with y prime on the same side. Now be careful here. Again, here, I should have showed an interim step. Notice this is 1 times cosine xy plus y prime cosine xy. You should multiply these out using distribution. Here we don't have any distribution. We're just going to put all the terms in front of the cosine or sine. So notice I have a y prime cosine xy, and I have a 2y prime cosine x. And so those are what I'm going to move over here. I'm going to move my negative y squared sine x to the other side by adding it, and the cosine xy will just stay there, the 1 times the cosine xy. Okay. Now I'm going to factor out my y prime, and then I'm going to divide both sides by the things that are left. 2y cosine x minus cosine xy. 2y cosine x minus cosine x plus y. And that's the answer to this equation. Again, I should have shown you this in 2 steps. Factor out the y prime, and notice you get 2y cosine x minus cosine x plus y, which we then divide both sides by it, and we get this equation. Notice we have no values, we have no points, so this is, when we're trying to find y prime, we're trying to find the function for the formula. Okay, let's try one more here. Now we're trying to find the second derivative of x to the 4th plus y to the 4th equals 16. Okay? We could probably actually, can we do this yet? I don't think we've got the substitution that we need yet. So we do need to do implicit differentiation with this. So again, the derivative of x to the 4th is 4x cubed. The derivative of y to the 4th, first again, the derivative with respect to y is 4y cubed. Add a y prime. And the derivative of 16, which is a constant, is 0. Again, you should be getting faster with these. When I solve this for y prime, I subtract 4x cubed, so it's negative on the right, divide by 4y cubed, and I get negative x cubed over y cubed. Okay, that's my first derivative. Notice I want my second derivative. My second derivative is the derivative of the first equation. I'm sorry, it's the derivative of the first derivative, right? The second derivative is the derivative of the first derivative, and so forth. So I now need to differentiate y prime. Notice I have a quotient, so I'm going to use the quotient rule. Okay? Could you do the product rule? Yes, if you change y cubed to y to the negative 3. All right? So again, remember we have the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all over the denominator squared. So this is a good step here. It's showing you kind of what we're doing versus actually doing anything. And do not forget, we have a negative in front. That's a coefficient, so we can take it out and apply it at the end. Do not forget these negatives. A good idea, especially on a test or on scratch paper, is to highlight negatives and to highlight minus subtraction problems so you don't forget to distribute. Okay? So notice I get y cubed times the derivative of x cubed is 3y squared. X cubed times the derivative of y cubed is 3y squared y prime, and this is all over y to the 6. Okay? So what I get here is negative 3x squared times x to the 4th plus, or y to the 4th plus x to the 4th over y to the 7th. And that looks pretty good. Okay? I've taken out my common factor, which is 3x squared, from both of these, and I get this x to the 4th plus y to the 4th. But notice, and this happens a lot when we're doing these multiple or higher order derivatives, especially with implicit differentiation, notice this is our original equation, x to the 4th plus y to the 4th. And so we already know that our original equation has an explicit value for this. X to the 4th plus y to the 4th will always equal 16. So we can substitute the value of 16 for the formula in the parentheses. And so this second derivative simplifies to just negative 48 x squared over y to the 7th. So after you've done your formula, pay attention to where you started and see if there's some substitution you can